Hello and welcome to a new video on IGCSE Classified Physics Paper 4. In this video, we shall be discussing heat transfer. We shall begin with basic questions. A footballer and a referee are discussing a puddle of water that has formed on the pitch. The footballer wears a white shirt, whilst the referee wears a black shirt, which apart from its color is identical. Figure 5.1 shows the two men looking at the puddle. The weather is bright and sunny. State and explain how the temperature of the white shirt differs from the temperature of the black shirt. Of course, we should know that black is a good absorber or emitter of heat. So in the summer, black absorbs more heat than white. So the white t-shirt or the white shirt will be cooler and the black shirt will be hotter, because white is a poor absorber of heat, whereas black is a good absorber of heat. State the names of the thermal processes by which the lamp transfers energy to the surroundings. So the lamp can actually transfer energy to the surroundings using all three processes: conduction, convection, and radiation. The most important process here is radiation. So this is what you must state. You must state radiation. And then you can either state conduction or convection. For conduction, you should understand that if something touches the lamp, it will immediately become hotter. If you touch the lamp with your hands, you will immediately feel the heat. So this is transferred by conduction. And for convection, you should understand the idea that the air around the lamp will be warmer and it will rise up, and cooler air will replace the air that rose up. So anything that creates heat can create a convection current. So for this question, you need to say radiation, definitely, and you can either say conduction or convection or both. Figure 4.2 shows a firefighter wearing shiny silver-colored clothing. State the benefit to a firefighter of wearing shiny silver-colored clothing. Again, white and silver are good reflectors of heat, but poor absorbers of heat. And this is important during firefighting because you don't want the body of the firefighter to absorb heat. You want to minimize the absorption of heat to save the firefighter's life. So it would definitely make sense to wear something that is shiny and white or silver colored. So we're going to say that shiny clothing is a poor absorber of thermal energy, and this reduces the thermal impact of fire on his body. State in terms of atoms what is meant by internal energy. So internal energy is the sum of kinetic and potential energy of the atoms inside any body. So we just need to state that it is the sum of kinetic and potential energy of atoms or molecules. Here they said in terms of atoms, so of course you need to say of atoms. A silver spoon has a thermal capacity of 7.2 joules per coulomb, per degree, joules per degree. The silver spoon is dropped into a saucepan of boiling water. The internal energy of the spoon increases as its temperature increases from 22 to 100 degrees. The spoon is removed from the boiling water and immediately it begins to transfer energy to the surroundings. The temperature of the surroundings is 22 degrees. Sketch a graph to show how the temperature of the spoon changes with time from the instant that it is removed from the water. So once removed from the water, it has a temperature of 100 degrees. So our graph should start at 100, and then it should gradually cool off until it reaches 22, because this is the temperature of the surroundings. So once it reaches 22, there will be no more thermal energy transfer. So you have to have a curve decreasing with time, needs to be concave up because it loses more temperature at the beginning. It decreases faster at the beginning, and then gradually it slows down as it approaches 22. Now we move on to more advanced questions. A beaker contains some water at room temperature. A student places a mercury in-glass thermometer in the water with the bulb of the thermometer just beneath the surface of the water. Figure 4.1 shows the arrangement. The student uses an electric fan to blow air across the open top of the beaker. She notices that the reading on the thermometer begins to decrease. Explain in terms of water molecules why the temperature of the water at the surface begins to decrease. So at the surface, for any hot liquid, what happens is that molecules that have highest kinetic energy are going to break bonds with other molecules, what we call intermolecular bonds, and they will escape from the surface, and this process is called evaporation. Seeing that the high energy molecules escape, the average kinetic energy of the remaining molecules is going to decrease. So because the highest kinetic energy molecules are going to escape, therefore the average of the remaining molecules is definitely going to decrease. You should understand that the temperature is a measure of the average kinetic energy. So if the average kinetic energy decreases, the temperature must decrease as well. And of course, the fan aids this process. It increases the rate of evaporation. In B, we are told the student places the thermometer near the bottom of the beaker. The electric fan continues to blow air across the top of the beaker. After some time, the student observes that the temperature of the water at the bottom of the beaker is decreasing. State the name of the thermal transfer method causing this and explain what is happening in the water. So we said that evaporation will make this part of the water cooler. So this is now cooler because of evaporation, because the average kinetic energy decreased. What happens if you have cool water at the top and warm water at the bottom? So you have something called a convection current. The warmer water rises up and the cooler water falls down. This is because warmer water is less dense than cooler water. It expands, so its density decreases, and therefore it rises up. This is called convection. So we're going to say that the cold water at the surface becomes denser, falls to the bottom of the liquid to be replaced by warmer water from the bottom. And this repeats until all the liquid cools down, and this is called convection. Figure 5.1 shows a cross-section of the inside of a vacuum flask containing a cold liquid. The walls of the vacuum flask are made of glass. The vacuum flask is being used to keep a liquid cool on a hot day. Explain how the labeled features of the vacuum flask keep the liquid cool by reducing thermal energy transfer. Include the names of the processes involved. So we have 4 labels, and we want to figure out what each label does to reduce the thermal energy transfer. Of course, anything that is silver has to do with radiation, because silver is a good reflector. It's a poor absorber. So silvered surfaces are going to reduce thermal radiation because they are poor emitters. Anything that is a poor absorber is also a poor emitter. The words that are in air quotes are keywords. They must be stated in the answer, of course. So you need to clearly state that they reduce radiation because they are poor emitters. As for vacuum, it can reduce conduction as well as convection. So you need to state conduction and convection in terms of vacuum, because the only method of transfer that works through vacuum is radiation. Finally, for the glass is a poor conductor, of course. It's a non-metal, it's a poor conductor. So it reduces the heat gain by conduction, and the stopper can reduce convection or evaporation, because the stopper prevents warm air or warm fluids in general from rising up. So therefore, it prevents convection, and it also prevents the escape of high energy molecules. So it prevents evaporation as well. In B, we are told suggest a suitable material for the stopper. Of course, the stopper can be made of either rubber or plastic or cork. These are the suitable materials for the stopper of a vacuum flask. Explain why houses in hot countries are often painted white. Use ideas about the transfer of thermal energy in your answer. So white, we said, is a good reflector and a poor absorber. And this helps with hot countries in the summer because it reduces the absorption of heat and therefore reduces the heat gain by the houses on hot summer days. As a star approaches the end of its life, the amount of radiation emitted from it per second changes. The star cools down. State any effect on the rate of emission of radiation. So you should understand that hotter objects will emit more heat energy by radiation. So the cooler an object is, the less radiation occurs. Radiation is expected to occur less in cooler objects. So the effect is simply that radiation decreases. A glass tube passes through a stopper and into a glass flask. Figure 4.1 shows that the flask is completely full of a liquid and that there is also some liquid in the tube. The flask is immersed in a large beaker of very hot water. At first, the level of the liquid in the tube falls, but after a short time, it rises. Explain why at first the level of the liquid in the tube falls. So this is kind of tricky because you're expecting that the level of the liquid is going to rise because you're placing it in some very hot water. So what happens when we place it in hot water? First of all, we expect that on the long run, the liquid will expand and it will rise up because it will occupy more space. So the level of the liquid will rise up. This is the answer actually to double I. This is on the long run. However, at first, the liquid level falls, and this does not immediately make sense. Why would the liquid level fall? This is because the first layer that is impacted by the hot water is actually the glass. So the first receiver of the hot water is the glass. So at the very beginning, the glass expands before the liquid expands. So when the glass expands, the tube, the whole device becomes bigger. And when the device becomes bigger, of course, the level of water inside it is going to necessarily decrease, or the level of liquid, I mean, inside it must decrease. So at first, the glass expands, so the liquid moves down, and then the liquid itself expands, therefore it moves up again. Now let's see the model answer to this. So at first we say that the glass of the flask is heated by conduction, so it expands and its volume increases, so the level of the liquid falls. And then in double I, we're going to say that the liquid starts to warm up and expands more than the glass, so the level of the liquid rises up. Two metal spheres of different diameters are heated to 900 degrees Celsius in a hot oven. The two spheres are removed from the oven. State and explain any difference in the initial rate of emission of radiation of thermal energy between the two spheres. Of course, the bigger an object is, the larger the surface area, the larger the rate of emission. So the larger metal sphere loses more heat by thermal radiation due to its larger surface area. One hot sphere is now heated in a hotter oven. State and explain any effect on the rate of emission of radiation of thermal energy from that sphere when it is removed from the hotter oven. So again, we said this before in this video, that the hotter an object is, the greater the rate of thermal radiation. So it will now have a greater initial temperature, and therefore it will exhibit greater thermal radiation. Finally, we move on to questions that have to do with experiments concerning heat transfer. Figure 4.1 shows a thick copper block that has been heated to 400 degrees Celsius. One side of the block is dull black, the other side of the block is polished and shiny. In experiment 1, the thermometer bulbs are both painted black. They are placed at equal distances from the surfaces of the block. The maximum temperature shown by each thermometer is recorded. Explain any difference between the maximum temperature shown by the two thermometers. So, of course, inside, it's the same temperature. It's a liquid, it's a copper block that has been heated to 400 degrees. So in the copper block itself, we have a temperature of 400 degrees. However, from the left here, we have a black surface, which is a good emitter or absorber of heat. So it will emit heat, it will create or produce or expel heat towards thermometer A. So we expect that thermometer A will record a greater maximum temperature. However, for the white surface, it's a bad emitter and absorber of heat. So therefore, thermometer B will not get the same effect. It will still get a temperature increase, but not to the extent of the side on the black surface. So not to the extent of thermometer A. So we say that the maximum temperature shown by thermometer A is greater than that shown by B, since the dull black surface is a better emitter of thermal energy than the shiny surface. So more thermal energy is transferred to thermometer A by radiation. Of course, radiation here is a key word. In double I, we're told in experiment 2, the thermometer bulbs are both shiny silver colored. They are placed at the same distances from the surfaces of the block as in experiment 1. State and explain any differences that are observed in the maximum temperatures shown by thermometers in experiments 1 and 2. So in experiment 2, we're going to repeat the process, but here instead of having dull black, we're going to have shiny silver colored bulbs. So As a result, we expect that if these are now silver or shiny, we expect them to reflect the heat coming from the copper. We do not expect them to absorb the heat. So therefore, we expect a smaller maximum temperature in experiment 2 for both thermometers. So in this case, we're not comparing A to B, we're comparing A and B in experiment 1 to A and B in experiment 2. We're comparing the two different experiments, where the only difference is that the bulb of the thermometer is shiny, not black. So now that it's shiny, it will absorb less heat, so the maximum temperature will be smaller. So that's why we say that the maximum temperature recorded in 2 is less than that in 1, because the thermometer bulbs will absorb less thermal energy when painted with shiny silver, since silver is a poor absorber of thermal radiation. Using the apparatus shown in figure 5.1, describe an experiment to demonstrate good and bad emitters of thermal radiation. Include the expected results and the conclusion. You may use a diagram. So we have 4 pieces of equipment, and we are required to design an experiment here to demonstrate good and bad emitters of thermal radiation. So it's very obvious what we're going to do. We're going to heat water to a certain temperature, and then pour the hot water into the bottle, and then place the 2 thermometers on either side of the bottle. And of course, for accuracy, we must make sure that the distance is the same, and this is ensured using the ruler. And then we're going to demonstrate that the thermometer on the black side will experience a greater increase in temperature because it's a good absorber of heat. So we must also understand that the thermometers must be placed near the bottle, otherwise the effect of radiation will not be very clear. So it has to be at a close distance from the bottle. So what we're going to say is pour hot water in the metal bottle, place the 2 thermometers near the bottle, one on either side of the bottle and at equal distances from the center of the bottle, and this is facilitated with the ruler. The thermometer on the black side will display a higher temperature than the thermometer on the white side, since black is a better emitter of thermal radiation. A student wants to investigate good and bad absorbers of thermal radiations. She has the apparatus shown in figure 5.1, a supply of cold water and a meter rule. Explain how the student could use the apparatus she has available to carry out her investigation. Describe the results she would expect to obtain. Draw a diagram of the setup. So here we have 2 cans. One of them is polished, one of them is black painted, and we have 2 thermometers, and we have an electric heater. Obviously, it's a very similar experiment to the one before. What we're going to do is we're going to pour equal volumes of cold water in the 2 cans, and we're going to measure the temperature change in this water. So the idea is that we have to place the cans at equal distances from the heater. So we would have a diagram like this. This is our heater. And we have the 2 cans on either side. And we would expect here that we would have to make sure that the distance is the same from the heater. And we would pour cold water into both cans. Water must have the same initial temperature, of course. And then what you would do is put the thermometers in the cans and measure the temperature change in each. And of course, we expect the black painted can to gain higher, to increase in temperature at a higher rate. So we're going to pour equal volumes of cold water in the 2 cans. And then we're going to place the 2 cans at equal distances from the electric heater. We ensure the equal distances using the meter rule. We put the 2 thermometers in the water in the 2 cans, and the result is that the thermometer in the black can will record a higher temperature than the thermometer in the polished can, because black is a better absorber of thermal radiation. This brings us to the end of our video. I hope this has been beneficial. Thank you for watching.